Okay, we're going to go through and review the different types of conics, and just wanted to remind you how to create them from a cone. So a circle is when you slice parallel to the base of the cone. That's the cross section, that's a circle. An ellipse is when you slice diagonally, but you do not go through the base of the cone. A parabola is when you slice diagonally and you do go through the base of the cone. And a hyperbola is when you're slicing through the two inverted cones and it has to be completely perpendicular to the base so that you're hitting both cones with your slice. So I kind of reviewed just the definition of a circle, set of points equidistant from a fixed point. And here is the conic standard form equation, your right and left, up or down, and x squared plus y squared equals your radius squared. So if I give you this form, you have to first put it into conic's standard form. If you notice here, you have a coefficient of 2 for both the x and the y squared, so you can actually divide the entire equation through by 2 before you start. So I'm going to divide everything by 2. So now I have x squared. I'm going to go ahead and move this term next to my x. So this is actually minus 2x. And then I would have y squared. And then I have plus 6y. And this negative 9, I'm just going to move over as positive 9 on the other side. So I kind of am trying to save a step here. Don't have a lot of room. To complete the square, you cut the b value in half, so that'd be negative 1, and then you square it. So add 1 to both sides of the equation. Cut 6 in half, so that's 3. 3 squared is 9, so also add 9 to both sides of the equation. So now I have x minus 1 squared plus y plus 3 squared. Looks like this equals 19. So the r value is the square root of 19. So the square root of 19, 4.4. So r equals 4.4. So I'm going to locate the center. I go right 1 and down 3. So there's the center of my circle, and I'm going to go 4.4 in each direction. 1, 2, 3. 1, 2, 3, 4.4. 1, 2, 3, 4.4. 1, 2, 3, 4.4. 1, 2, 3, 4.4. All right, an ellipse, this time it's a set of points, and it's the sum whose distances from two fixed points is constant. So if you remember, those two fixed points, if you had kind of a string stretched to them, and then you moved that string all the way around, right? This string, as it gets moved all the way around the circle, or ellipse, forms all the points. And so when you're looking at your equation, it's going to have the plus sign in between. That's how you know it's the sum. It's going to say equals to 1 over here, so you know that you're ready to read it. Still left, right, still up, down, but your a squared and your b squared value are going to be used to find the lengths of your axes. And if a is the bigger number, so if a is under the x, it would be a horizontally positioned ellipse, horizontal. If the a value, the bigger value is under the y, it's going to be a vertically positioned ellipse. We use this relationship between a, b, and c so that we can find the location of the foci, which I'll show you. And to find eccentricity, you take c divided by a. So let's graph this ellipse. So I'm going to go 3 and just 0. So 3, 0 is the center of this ellipse. This a squared value looks like it's under the x. So a is 3 and b is 2. I take the square root. So I'm going to go 3, 1, 2, 3, and dot the vertex 1, 2, 3, dot the vertex, and then vertically 1, 2, dot the vertex, 1, 2, dot the vertex. So there's my horizontal ellipse. To locate the foci, I'm going to plug a squared and b squared into this equation. So I have 9 for a squared, 4 for b squared, so that makes c squared 5. So if c squared is 5, c by itself is the square root of 5. The square root of 5 is 2.2. So the foci are always located on the major axis, which in this case is horizontal. So I'm going to go 1, 2.2 and put a dot, 1, 2.2 and put a dot. So those are my foci. And to find the eccentricity, I would take the square root of 5 and divide by a, which was 3. So the square root of 5 divided by 3 comes out to eccentricity equals 0.75. So that is fairly elliptical. Fairly elliptical. Because remember, an eccentricity of 0 would be a circle. Eccentricity of 1, which is impossible, is a pretty straight line. So the longer your ellipse is elongated, the closer to 1 this ratio is, like 0.8 or 0.9. All right, so here's another ellipse. And for this equation, we're going to have to put this in Conics standard form. And so this time I can't just divide through by 16. So I'm going to group together. I've got 16x squared minus 96x. And then I have 25y squared minus 200y, and then equals negative 144. I'm going to divide out this 16 from these two terms. So 96 divided by 16 is 6. So I really have x squared minus 6x. So I'm going to finish by adding 9 to complete this square. But what is 16 times 9? That's what I need to add to the other side. 16 times 9 is 144 that I'm adding. And then here I need to take out a 25. So that would give me y squared minus 8y. So I would also have to add 16. So 25 times 16 is 400. So I'm adding 25 times 16 to the other side. So now I have 16x minus 3 squared plus 25y minus 4 squared equals 400 exactly. And I'm going to go through and divide by 400 because I need to get 1 on the right-hand side so that this is in standard form. So 400 divided by 16 is 25. So I took 16 over 400, which is 1 over 25. And then y minus 4 squared would be over 16 equals 1. So I'm going right 3 up 1. Right 3 and up 4. Right 3 up 4. There's the center of my ellipse. The a value is 5. It's under the x. 1, 2, 3, 4, 5. So I'm going 5, 1, 2, 3, 4, 5. And then 1, 2, 3, 4. 1, 2, 3, 4. So here is my ellipse. And then it says also state the eccentricity. So I have to find a squared equals b squared plus c squared. So 25 equals 16 plus c squared. Pythagorean triple, so c squared is 9 and c is just 3. So from the center, 1, 2, 3, that's the location of the foci. And 3/5, which is 0.6, is my eccentricity this time. Okay, I wanted to briefly show you how to graph a hyperbola, or at least be able to identify the difference between a hyperbola equation and an ellipse equation. We did not spend a lot of time on hyperbolas. I'm not going to have you solve problems with the Pythagorean identity for hyperbolas. So you only have to know the one for ellipses. You don't have to write this one down. I'll always tell you if you need the C value. The C value just helps you find the foci anyway, so we can graph these without the foci. So the first thing you're going to notice is that this is a vertical hyperbola because y is coming first. So this time it depends on which term is in front of the minus sign, not which denominator is bigger. If you notice, the bigger value is actually over here. This is still a vertical hyperbola because the y value is positive. So I'm going to go right 4 and down 2. and locate the center of my hyperbola. And then in the vertical direction, I'm going to go 2. Square root of 4 is 2. So I'm going to go up 2. I'm going to write V for vertex, down 2. I'm going to write V for vertex. That's where my hyperbola is coming from. It's going to look like this at the end. Now I go 3 to the left and right. 1, 2, 3, put a dot. 1, 2, 3, put a dot. Those are not vertices. So I'm going to now draw a rectangle around those 4 points so that I can draw this kind of dotted line through the diagonals of that rectangle. So here is actually the hyperbola. So it touches that vertex, and then it touches that vertex, and it goes towards the asymptote lines. It'd be great if you knew how to write the equations of those asymptote lines, but I wouldn't stress about it. Point slope form, y plus 2 is plus or minus, would this go up 2 over 3? 2/3 x minus 4. So I'm not stressing the asymptote line, but it would be great if you knew, leaving pre-calculus, how to write the equation of a line in point slope form. I guess, did I only have you do one hyperbola? I guess so. So the hyperbola, if it had been horizontally, this just would have been flip-flopped and it would have opened the other direction. And I was going to look at this parabola. And so this time it's a set of points equidistant from a fixed point called the focus and a fixed line called the directrix. Like I said, parallel to the side of the cone. So when you're slicing your cone, it's kind of going down through the base. And if you have a vertical parabola, that's your old friend x squared. If you have a horizontal parabola, right, it's going kind of sideways. If the p-value is positive, a vertical parabola would open up. P-value negative, it would open down. Horizontal parabola, it would open right or left. 4p is the focal width. So let's take a look at what that means for this function. First thing, we need to get this 8 out of there so that I can actually read where the vertex is. So 8 is the 4p value, and this looks like we're going left 6 for our vertex, comma 0. So I'm going to go left 6 and put my vertex. So now if the 4p value is 8, that tells me that the p value is just 2. This is a sideways parabola that's opening to the right. So that tells me if I go 2 units to the right, that will be my focus, and 2 units to the left, that will be the line of the directrix, and the focal width is 8. So from the focus, we're going to put a dot that's up 4 and a dot that's down 4 because that's the focal width of the parabola at that point. And those are the only key points that you need to graph for the parabola. It would be great to know that a vertical line is just x equals -8. Okay, I've got 2 applications for you, and then you're going to complete the guided practice on the back. And obviously, conics aren't going to be a focus of your final exam, but there certainly will be several questions on conics. So if you're confused on them, reach out to me. Let's see, I did not mean to give you a parabola application. So I'm not giving you a parabola application. I'd like to change this to a tunnel problem. So I'm crossing this out. If you're watching the video, like I hope you are, let's say it's a tunnel and it spans 50 feet and it is maybe 20 feet at the center. I want to, it's a semi-elliptical. I want an equation and I want the height, let's say 5 feet from the center line. So if this is spanning 50 feet, that tells me that the A value would be 25. And 20 feet at the center tells me the B value is 20. So to write the equation of this ellipse, it would be just x squared plus y squared equals 1 if I center it right at the origin. 20 25 squared is 625, right? 625. 20 squared is 400. So once I have my equation, to find the height 5 feet from the center, all I do is plug in 5 where I see x. I'm going to solve for y. So I have 25 over 625 plus y squared over 400 equals 1. How do I get y squared by itself? I'm going to take the 25 over 625, subtract it to the other side on my calculator, and I'm just going to hang on to that 0.96. Then I'm going to multiply by 400 on both sides. So 0.96 times 400. Then I'm going to take the square root of my answer. So it's about 19.6 feet out when I'm 5 feet from the center line. So this right here is still 19.6 feet tall. And here's my second ellipse application where I'm finishing with this video. A whispering gallery, it has an elliptical ceiling. There's my elliptical ceiling. It has foci located 15 feet from the center. So that tells me that C is 15. The highest point of the ceiling is 20. How long is the whispering gallery? So I'm just looking for A, right? This would be A, and 2A is the length of the whole gallery. So I can use that Pythagorean identity, which is A squared equals B squared plus C squared. So A squared equals B squared plus C squared. A squared is what we don't know. B squared is 400, and C squared, 15 squared is 225. So A is the square root of 625. So the square root of 625, we already said, is 25. So A is 25. Oh, so if A is 25, the total length then is 50 feet long. So I guess that was a coincidence that I accidentally picked a similar ellipse for my tunnel problem, but they won't always come out with those same exact numbers. So now you are working on the guided practice, those 4 questions on the back page. Thanks.